I'm Foteini. I'm the SPIN-ESR 2.3, and yeah, as Celine said, I joined SPIN quite late. I joined this October. So today I'm going to introduce you to my project, which is on machine learning-based earthquake monitoring and forecasting, and which I'm doing at the University of Edinburgh and the British Geological Survey. And my supervisors are Margarita Segu and Brian Bapti from the British Geological Survey, and Ian Main and Andrew Curtis from the University of Edinburgh. So the motivation behind my project is the fact that recently there have been some supervised learning models that have been able to produce high detail earthquake catalogs. And so these catalogs are able to record at least a factor of 10 more earthquakes than traditional catalogs. And so these events that they have been able to recover are mainly events with of small scales, but as earthquake behavior seems to be scale invariant, it seems that we might be able to use these small events to inform earthquake forecasting for earthquakes of all magnitudes. And so the questions that I will be trying to answer within my project are: what can we learn about earthquake behavior from these detailed catalogs that we now have available? And how can these detailed catalogs improve probabilistic earthquake forecasting? So yeah, here is an example of a traditional catalog on the left and the deep learning catalog on the right. This is an example from the Amatrice earthquake in Italy, 2016. And yeah, we can see that on the right we have the deep learning catalog, which contains a significantly larger number of events and also has significantly smaller magnitude of completeness. So what I'm currently focusing on is the problem of short-term earthquake forecasting, which is essentially a spatiotemporal time series forecasting problem. So given an array of past earthquakes, I'm trying to determine whether it's possible to produce forecasts of the time and location of future events. And I'm trying to do this by using a data-driven approach. So I'm trying to train a model with the use of earthquake catalog data. And the goal is to then compare this data-driven approach with physics-based and empirical forecasting models in order to assess its performance and maybe even consider fusing different approaches to boost predictability. So in an initial experiment that I did, I used data from the Southern California earthquake data centers, earthquake catalog data, and I created daily maps of my data by dividing the spatial area that I had into bins and then counting the number of events with magnitude larger than 3 in each grid cell. And this was, these daily maps were my model's input. And so I used a deep learning model for this experiment, which consists of an autoencoder and a transformer. I'm not going to go into too much detail about this, but what the model does is it takes these daily maps as input and then first passes them through a convolutional encoder to transform them into 1D vectors, which are then passed on to a transformer model who performs the final the predictions in the format of 1D vectors. And these 1D vectors are then passed through a convolutional decoder to produce the final time series forecasts. So yeah, and finally, this is just an initial result that I have been able to get from this model. So this is an example forecast for 6 consecutive days using the previous 6 days as input. And in the top row we have the actual ground truth data, and in the bottom row we have the model's outputs. Yeah, this was just an initial test, and yeah, in the future we will probably reduce the time scale to 1 day ahead predictions. So yeah, that's it for me. Thank you.